Welcome back, ladies and gentlemen. So we've reviewed vector addition, 2 dimensions, and complex vector addition. Now we're going to be moving on to what I was already talking about and mentioning last video. We're going to be doing vector addition with velocity. Now, as I showed you in the last video, there's no real difference between the vector addition of distance and velocity, at least not mathematically. I'm going to demonstrate that further with an example here. So in the notes, we can check it out, and we talk about the fact that we have a river, and we have a north-south river, and that river is 80 meters wide. So we can start drawing out our puzzle here, our picture, and we can put this together. All right, here's our water, and this is the velocity of the river. Here's the banks of the river, right, on the sides, and we know that the distance, the separation from one side of the river to the other is 80 meters. All right, what else does the question say? You'd like to swim across and can manage a constant 8 meters per second when you swim. Okay. So you can go 8 meters per second. Let's make you not blue. Don't want you the same color as the river. We'll make you red. So here you are, and you're like right over here, and you're going to go swimming. So let's give you a pair of goggles. And you want to get from here across the river to there. And it says that you can go at a nice constant 8 meters per second. So the velocity of the swimmer, the velocity of you. First question, how long will it take to cross the river? Usually everyone gets this one wrong. They end up making it too complicated. It's not. Think carefully about what the question is asking. How long will it take you to get from here to there? Well, if there was no river in the way, right? It's high summer, the river's dried up. How long would it take you to get from here to here? Well, they're separated by 80 meters, right? So I got to travel 80 meters. I can manage 8 meters a second. It's going to be 10 seconds, right? Like this separation here is 80. I move at 8, so that'll take 10. Seems pretty straightforward. Seems suspiciously straightforward, Mr. C. So time to cross. So, okay, fine. Let's do this. The velocity initial is going to be 8 meters per second. The velocity final is still 8 meters per second. Acceleration is 0. The displacement is 80 meters, and the time is what we are looking for. So my equation, d equals VIT plus AT squared over 2. This goes to 0. The distance, or the displacement, is 80. My speed is 8. Time will be 10 seconds. Okay, that seems reasonable. So what does the river do? It says here, the river has a current running of 6 meters per second. Oh, okay, so now we have a river current. 6 meters per second, and of course it is going south, because the river is going from north to south. Oh no, the question says that the river current is going north. Silly me. River current is going north. So we'll just adjust that arrow to go that way. So when you're in the water, the river current is going to push you, right? That makes sense, right? If I just step in the water, the current is going to carry me downstream. That's how current works. That's why, for example, water goes towards the ocean. So how far is the river going to push you? How far is the river going to push you? Well, think about it, right? Do we care? Like, what numbers do we need, right? Let's frame that way. What numbers do we need? Well, the river's got a velocity of 6 meters per second north, and it's constant, right? There's no acceleration. I'm looking for d, but what's scrunched up at the bottom of the page there? What is the time? How long will the river push you along? Well, is the river pushing you when you're not in the river? No, right? Like if I'm on the shore over here and the river's over there, if I'm over here, the river doesn't do anything to me. It's only once I jump in the river that now the river starts to pull me along. So how long am I in the river? 10 seconds. Why am I in the river for 10 seconds? Because once 10 seconds have passed, I have gotten out of the water, right? I've reached the other shore, I grab a hold of the bank, and I pull myself out. So the river can't push me anymore. So these two questions share a time. They're otherwise independent of each other, right? Like the only connection between my motion and the river's motion is the time that it takes for me to get across. As a result, well, d equals 6 times 10. So d equals 60 meters. So the river is going to push me 60 meters with the current. Let's take a look at our diagram. What does that look like? You went straight across. You went like this. And the river pushed you like that. It's almost a straight line. Well, well, well. What do we see here? A two-dimensional vector with an angle. Well, we know what to do with that. So it shouldn't be a surprise when I ask you, what is the total displacement of the swimmer? Right? We know what these two numbers are. We know that this is a 60-meter displacement, and we know that this one down here is an 80-meter displacement. So we can find what the total displacement is, right? The green vector, the resultant vector, if you remember that terminology. All we have to do is take our information and solve it. So what is the total displacement? Well, what do? We take our 60 squared and our 80 squared. We're going to have to square root that in order to get C. C is going to be equal to, let's get on our trusty calculator, 60 squared plus 80 squared. That's going to be, it's going to be 10,000. Square root of 10,000. We're going to get 100 meters. 100 meters. Okay, that's pretty straightforward. Oh, we need angle. Tan theta equals opposite, which is 60, over adjacent, which is 80. So we're going to go 60 divided by 80 equals 0.75. Second function tan, where is that on this calculator? Oh, I legitimately can't find it on this calculator. Well, that's inconvenient. It's a good thing I did the math in advance. We get an angle of 37 degrees. 37 degrees. This is going to be north of east again. So what's our total displacement by the swimmer? Their total displacement from where they started is 37 degrees north of east. I think that makes sense, right? we've put all this together and we've seen, this is all stuff we've done before. We did two separate one-dimensional calculations. We've got two different distances or displacements, and now we have found the resultant or the two-dimensional displacement of this person. And I think it makes sense, right? Like if you're swimming across the river and then the river's pushing you at the same time, obviously you're going to end up somewhere different than if you were just walking along a straight road. But you'll notice, of course, that so far we haven't done anything with velocity. So why don't we try that? What is the average velocity that describes the swimmer, and the river? Basically put, what is the green line? Well, I can do that because I know that the swimmer is going at 8 meters per second, and I know that the river is going at 6 meters per second. So finding this average velocity, well, that shouldn't be very hard. I just take my two pieces and I solve them. 6 squared plus 8 squared square root equals c. And again, the reason I can do this is, as I showed you in the first part of this video, it doesn't matter what the units are. They're vectors. Vectors are added the same way no matter what they are. So once again, I take my 6 squared plus 8 squared. It's going to give me 100, so the square root of 100 is 10. Meters per second. And, well, what's the angle? If we work it out, pretty sure you're not going to be surprised. It's going to be the same angle, right? Because I go from here to there. It's the same number. Why? Well, let's take a look. Tan theta equals 6 over 8. That's the same as 60 over 80, right? Like, I'm just removing a 0 here. If you remove a 0 from the thing, it doesn't change anything about the result. So this angle here is still going to be 37 degrees north of east. So in order to go 100 meters in 37 degrees north of east in 10 seconds, you have to travel at 10 meters per second at an angle of 37 degrees north of east. I don't think that's a big ask, right? If I want to go 100 meters in 10 seconds, I have to travel at 10 meters a second. How else am I going to do it? So what do we see here, right? These two different things with displacement and with velocity, they're treated exactly the same. There's no real change. The only thing that we've done is we've just put an S here. That's it. We put a /S. Without that, like if I cover that up, there you go. These two are basically the same thing, right? I'm just missing the 0 here. So that's the only change. So we can treat velocity and displacement as pretty much the same thing for the purposes of two-dimensional addition. Now, one thing that students do tend to get a little confused here is that they go, well, wait a second, if he's moving at 10 meters per second, why did he take so long to cross the river in that first question, right? Why did it take him 10 seconds? And there's a little note here in the notes, a note in the notes about the notes. The average velocity is higher, but it still takes 10 seconds to cross the river because the river doesn't make you go faster left and right. It only pushes you up in this case. This results in the very important distinction that motion in one dimension does not affect motion in the other. Right? How fast I go this way has no bearing on the river pushing me like this. Right? Like, always, students are like, but the river's pushing you. Isn't it going to make you go faster? Well, no, because the river's pushing you north and you're trying to swim east. Let's flip it around. The river is going at 6 meters per second. When you get into the river and start swimming, you're going at 8 meters per second. Do you make the river go faster? Right? You're in there swimming. Do you make the water move faster because you're there? No, the river stays the same. Similar, just because you're in the river doesn't change you. The only effect the river has on you is that it happens to be pushing you this way at the same time that you're going this way. The only connection between these two things is time. That's it. So we can take this a little bit further. Because you'll notice here, right, that we started here, but we didn't end up at this red X. We ended up over here. Because as we were swimming this way, the river was pushing us this way. So you can sort of picture it like this, right? Every single, let's draw another copy of the river here. Yeah, let's get some space over here. Every single second that you're in the water is going to move you. Right? So here we are in the water again. And you jump in and you swim to there. Right? There's our 1 second of swimming. Well, the river's going to push you up at the same time. Then you're going to swim, and the river's going to push you up at the same time. And then you're going to swim, and the river is going to push you up at the same time. So you end up following a path that I can loosely call a straight line, like so. That's what's happening second by second. But remember, when it comes to vectors, we can rearrange the order that we add them in. I can add all the red ones together all at once. So I can just be like, okay, there's a red one down here and a red one there. And I just remove them from a little higher up. Similar, I can take the blue vectors and just slide them all over to the end. There's a blue one here and a blue one there. And I just remove them from the middle, and there's our triangle. So that's all that we're doing here, right? So how in the world do we go from here straight across? We'd need to find some way to cancel the river out, right? Because the river's pushing us north. We don't want to go north. We want to stay in exactly the same line. Think about it second by second, right? I went here, the river pushed me up. So if I just go straight across, the river will be able to push me. I don't want the river to push me, so I can't go straight across. I want to do this in 1 second. The river is going to push me like that. So what do I have to do? I have to go down like this. I swim down, the river pushes me up. I swim down, the river pushes me up. I swim down, the river pushes me up. The result is a straight green line across. Well, almost straight. But what would that look like? Add the vectors. Remember, just like we did, we just slide them down to connect all the red ones together. So I got a red one here and a red one there. And I slide all of the blue ones over. Now, all right, in this case, they're all stacked on top of each other, but they'd all add up like so. Ta-da! It's another triangle. The difference is now I swim down at an angle and the river pushes me back into alignment of where I wanted to go. You're basically using part of your swimming to cancel out the current. But what angle do we need? That's tricky. But think about what these numbers mean. The red line is the swimmer. How fast can the swimmer go? 8. So this is going to be 8. How fast does the river? Well, that's 6. Well, we can do this. It's no longer a tangent, though, but we can do it, right? I'm looking for this angle here. And that's going to be hypotenuse, right? It's the long side. And this one over here is going to be sine. So this is going to be a sine because it's opposite. So we get 6 over 8. Now, in terms of what this ends up doing for us is that, I mean, realistically, it's not super hard. Obviously, the big tricky part here is that most people, when they see this, they're going to want to make this one the swimmer, because that's what we did in the other part of the question. But now we're in a different position. We're doing something a little different. So we just have to make sure that we put the numbers in the right places. But, you know, that's always been a problem for what we're doing. Okay, so we've got this here, and we're going to solve it. Now, once again, I don't know quite where the sign button is on this calculator. Usually they're really obvious to spot. So this must be a calculator for not trigonometry, but something else. It's okay, though. I worked it out in advance. 6 over 8 sine, that ends up turning into an angle of 49 degrees. Oh, but which way? South of east. Okay, so look what we've worked out. we've now figured out how to make it so we go directly across the river because we're making sure that the vectors add up. Now, for most of us in our everyday life, we don't really need to worry about this. We don't need to make sure that we end up directly across a river. We can just swim, whatever. But like, what happens if there's a waterfall and you need to swim? Don't swim near a waterfall, guys, but what happens if there was? Or a more realistic idea, what happens if you had a boat, right? If you have a boat, you don't, and the dock is here, you don't want to end up over there. You want to end up straight across. So what are you going to do? You're going to angle yourself down so that way you can sort of like line up, right? You seeing how this works? Because I'm going this way, the river pushes me up. This way, the river pushes me up. This way, the river pushes me up. I end up right where I need to be to put my boat away. To dock the boat. Put the boat away? What am I doing? So yeah, this is the big trick to this. The addition here, the actual math, is exactly the same as everything we've already done. It's only about how to properly interpret the math, how to set up the question. So, next question for us. How long will it take to cross the river? What is it? Isn't it going to be 10 seconds again? Oh, wait, it won't. It was 10 seconds because my 80-meter river was being crossed at 8 meters per second, but I'm not going 8 meters per second across the river anymore, am I? Remember what I said. Motion in one dimension does not affect motion in the other. The only thing I care about is the speed at which I go this way, right? The river doesn't care how fast I go down. All that's doing is canceling out the 6. I need to figure out how fast I'm going this way. How am I going to do that? The green vector, Pythagoras. I know this side of the triangle, I know this side of the triangle, I can find the missing side of the triangle. Okay, so we're going to do 6 squared plus a squared equals 8 squared. Wait, what happened there? Almost every other time, like literally every other time, it was a squared plus b squared, and we would put in the 2 numbers we had for a and b. But you got to remember, the c squared by itself over there in Pythagoras, that's the hypotenuse, right? And we have the hypotenuse. It's 8. So this slightly changes the question because we're going to do 8 squared, which is going to be 64. And once you get 8 squared, you're going to get your 64. And then you're going to get a squared, don't know what that is. And then here, your 36. Okay, well, I got to get a by itself. So I'm going to move the 36 over. That's going to become a squared equals 64 minus 36. So every other time you add it, but in this one instance, you end up subtracting it, just to be a little difficult. So there it is, and we take the square root of that. If it was cooperating, and we get the a of 5.3 meters per second. So this number is 5.3 meters per second. That is how fast I'm going horizontally across the river. What does that really mean? Well, originally I was traveling at 8, but I'm using up some of my speed to cancel the river out to make sure that I don't end up going with the river. So I'm going to be moving effectively slower. Now at this point the question becomes pretty straightforward because the distance is still 80. So this whole thing still becomes 80 equals, now it's 5.3 t. So I take 80, divide it by my 5.3, and I get 15.12 seconds equals time. So it's going to take me 15 seconds to cross the river when I'm fighting the current. That's longer, but not a lot longer. I mean, it's only 5 more seconds, but I think that probably makes sense, right? Like if I'm fighting the current, if I'm going against the river the whole time, logically I'm going to be going slower because I'm not putting in all of my effort into going across the river. So the net result is that everything slows down a bunch. So again, The mathematics we're doing is pretty straightforward. Obviously, this one here meant that we needed to put things in a slightly different order because I've drawn a slightly different triangle than normal, but it's all stuff we've done before. It's nothing new. So let me summarize everything here, okay? So, right, step one, two-dimensional velocity is exactly the same as two-dimensional displacement, right? Doesn't matter if we were looking for meters or meters per second, it was the same technique. Motion in one dimension is independent of motion in the other. With the only thing that connects the horizontal and the vertical here is time. That's the only thing that connects it. Heck, there is a little activity, a little exercise that I usually try to do in class to showcase what I mean by the motion being independent. Let's see if I can do it. So what's going to happen is I have two markers here. See if I can do this on screen. This is going to be tricky. Is that I'm going to drop one, so it just falls, and I'm going to throw one sideways. The one that's going sideways, of course, is going to be moving horizontally. But gravity still pulls it down. And what I'm going to show you is that, hopefully, assuming I do it right, going sideways has no effect on gravity's ability to pull it down, right? Like if I throw this sideways, gravity still pulls the same as if I drop it. That's what I'm trying to say. You will see on your screen, they both reach the bottom of the screen at the same time. It doesn't matter that one of them was going like this and one of them was going like this. There's no connection between the two, except time. That's about it. This is the fundamentals of all of this stuff. There's not a lot. But the plus side is that we kind of already remember how to do vector addition. We just need to, put it together. Okay, I'm going to leave it with there. We've talked about the mathematical side of this. Next video, we're going to talk about what all of this stuff looks like. And what we're going to find is that the perception of two-dimensional velocity is quite a bit different than the mathematics of two-dimensional velocity. But that will be for next time.